Welcome to the deep dive. Today, we're plunging into something that, well, it's everywhere, isn't it? Artificial
It
intelligence.
really is. From movie suggestions to, finding your way across town.
Exactly. We interact with these smart machines constantly. But have you ever really stopped to think, how do they actually get smart? How
hmm
do you go from just raw data, a pile of information, to something that can spot a cat in a photo, or translate languages, or even beat a world champion at Go?
Well, that's precisely what we're going to unpack in this deep dive. It's our mission, really.
Right.
We're looking at the fundamental steps. How you train an AI model,
Mm.
right from the very first piece of data it sees,
Mm-hmm.
through all the complex math it does, all the way to how it actually refines its performance. It's a step-by-step journey.
And we've got some solid sources guiding us.
We do. We're drawing insights from the 100-page machine learning book by Andrei Burkov and also Architects of Intelligence by Martin Ford. They'll be our guides.
Great. So let's unpack this. Bringing in AI from zero to smart. Where do we even begin?
We start at the absolute foundation,
Yeah.
data.
Right. Data. But for an AI, data isn't just like a spreadsheet we look at, is it? It's more specific.
Much more specific.
Yeah.
It has to be formatted in a way the machine can actually process. Think of it as a feature vector.
A feature vector. Okay. Like an input.
Exactly.
Hmm.
The input, we often call it X, and the AI uses that X to figure out a label, the output, which we call Y.
So input X leads to output Y. Simple enough?
Conceptually, yes,
Huh.
but that mapping is crucial. It's how machines translate the messy real world into something structured they can work with.
Turning messy stuff into insight. Got it.
And the sources give some really good examples, like if you're building a model to predict cancer,
Okay.
the feature vector X might describe a person, their age, medical history, maybe some genetic markers,
Uh-huh.
and the model outputs Y, which is the probability of cancer.
Yeah.
Or think about email. The feature vector X describes the email message, and the model predicts Y, is it spam or not spam?
Makes sense. It needs the right input for the output you want. But I'm wondering, what if your data isn't all numbers? Like colors, red, yellow, green, or days of the week? How does a machine deal with that?
Algorithms like numbers, right?
That's a great question. And you're right, algorithms thrive on numbers. So that's where techniques like one-hot encoding come in.
One-hot encoding.
Yeah, it basically transforms those categories like colors into several binary features, numbers.
Binary, like zeros and ones.
Exactly. So if you have red, yellow, green, one hot encoding might turn red into, say, 100. Yellow becomes 010. Green is 001.
Okay. So it converts categories into a numerical format the algorithm can actually use.
Precisely. It makes it digestible for the math that's coming later.
And what about, real-world data? It's always messy. What if pieces are missing?
Yeah, data's rarely perfect. There are a few ways to handle that.
Like what? Well, you could just remove the examples that have missing bits, but, well, you need a lot of data to afford doing that.
Right, you might lose too much.
Or you could use an algorithm that's specifically designed to handle missing values. Some can.
Okay.
Or another common approach is data imputation. That's basically filling in the gaps.
How? Like guessing.
Sort of. A simple way is just replacing a missing value with the average value for that feature across all the other examples.
Okay, so find the average age and plug that in if someone's age is missing.
Something like that. It's about making the data usable without distorting it too much.
All right, so we've got the data cleaned, formatted, maybe imputed. It's ready. Time to train.
Almost. There's one really crucial step before the actual learning starts. We need to prepare the data set itself.
Prepare it how?
We split it, usually into 3 parts.
Great, okay.
The training set, the validation set, and the test set.
Training, validation, test. What's the breakdown?
Well, the old rule of thumb was maybe 70% for training, 15% for validation, 15% for testing. But now, with, big data, millions of examples, it's often more like 95% for training, and then maybe 2.5% each for validation and testing.
Wow, 95% for training. Why split it at all then? Why not just throw everything at the training?
That's the key question. It's all about making sure the model learns to predict well on new data it hasn't seen before.
Not just memorizing the answers it saw during training.
Exactly. That gets us to a huge potential pitfall. Overfitting.
Overfitting, I've heard that term.
Yeah. Imagine a trivial algorithm could just memorize every single training example perfectly. 100% accuracy on the training set.
Sounds great.
But it would be completely useless in the real world. It hasn't learned anything general, it just memorized.
Like cramming for a test by just memorizing the practice questions?
Precisely. Then you see a new question on the real test, and you're lost.
So if you trained a car recognizer on only 10 specific pictures of cars,
It would probably fail miserably on any other curve pictures. Yeah. That's overfitting. We need to test it on data. It's never seen the validation and test sets to see if it can generalize.
okay, that makes sense. Data prepared, split correctly. Now, the AI's brain, how does it actually start thinking or, well, learning?
Right. So at the core, many AI systems, especially older ones, were inspired by biological neurons. Think of the perceptron.
The perceptron, a basic building block.
Kind of, yeah. It takes several numerical inputs, multiplies each by a weight.
A weight, like how important that input is.
Exactly. Then it sums them all up. If the total sum hits a certain threshold, it fires. It outputs a 1. Otherwise, it outputs a 0.
So it's like a little decision maker.
A very simple one. And those weights in that threshold, those are the parameters. Those are the things that AI actually learns by adjusting them during training.
The knobs it can turn to get better.
You got it.
And if you connect lots of these perceptrons together,
You get a neural network. Stack
Yeah.
them in layers.
layers. Okay. And is that what deep learning is? Just lots of layers?
Pretty much. Deep just refers to having many layers in the network. That depth lets it learn really complex patterns.
But it's not just about stacking them, is it? There's something else.
Right. The crucial thing is the nonlinear activation functions within the layers.
Activation functions.
Yeah, they introduce nonlinearity. Without them, even a super deep network would just be doing simple linear calculations. It couldn't learn the complex, wiggly relationships you find in real-world stuff like images or language.
Okay. So the depth and the nonlinearity are key for handling complexity.
Absolutely.
So the AI has its structure, its neural net. It starts with some parameters, maybe random ones.
Often random, yes, or based on some initial guess.
And it sees an input from the training data. What's the very next step in the learning loop? It makes a prediction.
It makes a prediction, it applies its current weights and biases to the input, and produces an output, a guess.
And then,
Yeah.
how does it know if it's right or wrong?
That's where the loss function comes in, or sometimes called the cost function.
Loss function, measuring the error.
Exactly. It calculates how wrong the prediction was compared to the actual correct label from the training data.
So if it predicted spam +1, but the email was actually not spam, the loss function measures that gap.
Precisely. And the goal of training is usually to minimize that loss, to reduce the error, though sometimes, like in logistic regression, the math is framed as maximizing the likelihood of the data given the model. But it's effectively the same goal, finding the best fit.
Okay, so the model makes a guess, calculates its error, it knows it messed up. What then? How does it fix itself? Does it just randomly tweak its weights?
No, not random tweaking. That would take forever. This is where the core learning mechanism comes in. Gradient descent.
Gradient descent sounds mathematical.
It is, but the idea is intuitive. Imagine you're blindfolded on a mountainside, and you want to get to the lowest point in the valley.
Okay.
You can feel the slope of the ground right where you are, right? The gradient, the steepness. Right. The gradient tells you the steepest direction downhill from your current spot. Gradient descent is the algorithm that tells the AI which way to adjust its parameters, its weights and biases to go downhill on the loss function.
To reduce the error most effectively.
Exactly. It takes a small step in the direction that reduces the loss the most. It's the AI's guide to getting better.
Okay, that makes sense. It's not random, it's guided by the error. Now, this seems like where backpropagation fits in. I feel like that's a big one.
It is the big one,
Yeah.
especially for deep neural networks. Backpropagation is the algorithm that makes training these deep nets practical.
How does it work?
Essentially, you calculate the error at the very end, the output layer,
Right, the laws.
and then backpropagation figures out how to distribute that error backward through all the layers of the network.
Backwards.
Yeah. It calculates how much each weight and bias in every layer contributed to the final error, and then it adjusts each weight and bias proportionally. If a weight contributed a lot to the error, it gets adjusted more. If it contributed less, it gets adjusted less.
So it's like assigning blame backwards through the system.
That's a pretty good way to think about it.
It's a gradual, iterative process. You do this over and over with many examples from the training data, and the network slowly refines its weights and biases, getting better and better.
That iterative error correction, that really unlocked deep learning, didn't it?
It really did. It was a crucial piece of the puzzle.
It's funny, thinking about the early days, you mentioned perceptrons. Some
Yeah.
people back then made some Well, wild predictions based on that early stuff, right?
Oh, absolutely. Ridiculous predictions sometimes. After the first perceptrons in the 50s, you had forecasts of machines that would walk, talk, see, even be conscious very quickly.
Yeah.
And when those predictions didn't pan out, you got the AI winters.
Right. Periods where funding dried up, interest waned. Exactly. But thankfully, fundamental research, including work on things like backpropagation, continued quietly in the background during those winters, laying the groundwork for what we see today.
Okay, so gradient descent and backpropagation are tuning the weights. But we talked about overfitting, just memorizing. How do we actively fight against that during training, beyond just splitting the data?
Right. We need more tools. That's where regularization techniques come in.
Regularization, making it more regular.
Kinda. It adds a penalty to the loss function for making the model overly complex. It discourages the model from fitting the training data too perfectly, especially the noisy parts.
How does it penalize complexity?
Techniques like L1 and L2 regularization add a term based on the size of the weights. L1 tends to push some weights all the way to 0, effectively selecting the most important features, making the model sparse.
Oh, interesting. Feature selection built in.
Yeah. L2 penalizes large weights too, but less aggressively towards 0. It often gives smoother results. And for neural nets specifically, there's a very powerful technique called dropout. During each training step, you randomly drop out, temporarily remove some of the units, neurons, in the network and their connections.
Randomly. Why?
It forces the network not to rely too heavily on any single unit or pathway. It has to learn more robust, distributed representations. It's surprisingly effective at preventing overfitting.
So it's like forcing teamwork and preventing any one neuron from becoming a superstar know-it-all.
That's a decent analogy. It encourages robustness.
So it's about finding this balance, right? Learning the real patterns, but not the noise. Not too simple, not too complex.
Exactly that. Finding the sweet spot. And that balance often depends on setting things other than the weights and biases.
Other things. Like what?
Hyperparameters. These are settings you choose before training starts.
Not things the model learns itself.
Right. Things like the strength of that regularization penalty we just talked about, or the learning rate for gradient descent, how big those downhill steps are.
And getting those right is important.
Absolutely critical. Choosing good hyperparameters can make the difference between a useless model and a state-of-the-art one. It often feels like an art form, or some people even call it alchemy.
Alchemy.
Really? Well, it often requires a lot of experience, intuition, trial and error. The sources mentioned there might only be a few hundred people worldwide who are really good at tuning these complex deep learning models.
Wow. That sounds like a bottleneck. Is there any way to automate that art?
Yes, definitely. That's a big area of research.
Yeah.
Systems like Google's AutoML are trying to do just that.
ML.
Yeah. It basically automates the process of trying out different model architectures and hyperparameters. It runs lots of experiments automatically to find the best configuration for your specific problem without you needing to be one of those hyperparameter tuning wizards.
Making it more accessible. That's cool.
Exactly. Democratizing AI development.
Okay, now, everything we've talked about so far, training sets with labels, loss functions, measuring error against those labels, that sounds like supervised learning, right? Where the teacher provides the answers.
Correct. That's the dominant paradigm right now.
But what if you don't have labeled data? Which is often the case, isn't it? Getting labels is expensive.
Very expensive, and that's where unsupervised learning comes in.
Unsupervised. No teacher.
Right. The AI learns from unlabeled data.
Mm-hmm.
It tries to find patterns, structure, group similar things together. It's called clustering.
Just finding inherent structure in the data itself.
Exactly. It's much harder in many ways, but also seen as a really important path towards more general AI. Because, well, that's how humans and animals seem to learn a lot, just by observing the world.
Interesting. Okay, so supervised has labels, unsupervised doesn't. What about learning by doing, like trial and error?
Now you're talking about reinforcement learning.
Reinforcement learning, okay.
Here, the AI, often called an agent, learns by performing actions in an environment, maybe a game, maybe a simulation. And instead of explicit labels, it gets intermittent rewards or penalties based on its actions. Did it achieve the goal? Did it crash?
So feedback comes later, not for every single step.
Right. Just a reward signal.
Yes.
Think about teaching a robot to kick a ball. It might just flail its limbs around randomly at first.
Yeah.
But if it happens to nudge the ball forward, it gets a small reward. Over time, through trial and error, guided by those rewards, It learns the sequence of actions needed to kick the ball effectively.
That sounds like how AlphaGo learned, the AI that beat the Go world champion. Didn't it learn by playing itself?
Exactly. AlphaGo, and especially its successor AlphaGo Zero, used a combination of deep neural networks and reinforcement learning, something called deep Q networks.
Deep Q networks.
AlphaGo Zero is amazing because it started with no human game knowledge, just the rules. It learned purely by playing millions and millions of games against itself.
Wow.
It would make moves, see the outcome of the game, win or lose the reward, and update its neural network weights based on that outcome. Continuous self-improvement through self-play.
So it iteratively got better just by playing.
Precisely. And that iterative nature is important too. Some advanced systems can be trained iteratively. You don't always have to retrain from scratch when new data comes in. You can update the model in batches.
That must be way more efficient.
It can be, yeah.
So we've journeyed from data prep through learning loops with gradient descent and backprop, regularization, different learning types. Let's pivot a bit to the real world. What are the big implications and challenges here? One thing seems obvious: the need for tons of data.
Oh, absolutely. Deep learning is incredibly data hungry. The sources mention needing armies of human annotators just to create the labeled data sets for supervised learning.
And that reliance creates problems, doesn't it?
Big time. First, bias. If the humans labeling the data have biases, or if the data itself reflects societal biases.
The AI learns those biases too.
Exactly. It just learns the patterns in the data it's given, warts and all. And second, distribution shift. If the training data looks different from the real-world data the AI eventually sees.
Like the car example trained on blurry backgrounds struggles with clear photos.
Precisely. Its performance can drop dramatically if the real world doesn't match its training world. Garbage in, garbage out, or maybe biased data in, biased results out.
Right. And when it does work, deep learning can seem almost magical. But then there's this black box problem. We don't always know why it works or why it fails.
That's a huge area of concern in research, because these systems learn statistical associations, not necessarily causal relationships or concepts the way humans do. They can be surprisingly brittle. You get these adversarial examples. Tiny changes to an input, often totally imperceptible to humans, that can completely fool the AI.
Like what?
The sources mention things like specific patterns printed on eyeglass frames, tricking facial recognition. Or small stickers placed on a stop sign, making a self-driving car system misclassify it. Even subtle digital alterations to an X-ray image that can make it falsely indicate cancer.
That's terrible.
It highlights that these systems perceive the world very differently than we do. They lash onto statistical patterns, not necessarily meaningful features in the human sense. Their understanding is alien.
Which leads to the big question: how close are we to, real AI, human-level intelligence, artificial general intelligence, AGI?
Well, based on what we've discussed, today's AI, especially deep learning, is incredibly powerful but very narrow.
Narrow, meaning task-specific.
Exactly. It can be superhuman at recognizing patterns in images or playing Go or translating text. But it struggles immensely with things humans find easy. Common sense reasoning, abstraction, analogy, transferring knowledge from one domain to a completely different one.
Right, learning one thing and applying it somewhere else.
That ability to generalize abstractly is a huge gap.
The sources mention an example, Bongard problems.
Yes, Bongard problems. They're visual puzzles designed specifically to test abstract reasoning. Humans can typically figure them out after seeing just a dozen examples.
Okay, and AI.
Even the best neural networks, trained on tens of thousands of examples, perform barely better than random guessing.
Wow. That really puts it in perspective.
It really does. It emphasizes this fundamental gap between pattern recognition, even sophisticated pattern recognition, and genuine, flexible, human-like understanding and reasoning.
So superhuman in narrow tasks, but still far from broad human-like intelligence.
That's the current state. Achieving that broader cognitive ability, that general intelligence, remains one of the biggest open challenges in the field.
So we've taken quite the journey today. From raw data needing structure, through splitting it up, the learning loops with guesses and corrections via gradient descent and backpropagation.
Avoiding pitfalls like overfitting with regularization and dropout.
Tuning those tricky hyperparameters, maybe even automating it with AutoML.
Exploring different ways to learn supervised, unsupervised reinforcement learning like AlphaGo.
It's an incredibly intricate process, this dance of data, algorithms, refinement. It's amazing how we've managed to get machines to achieve so much.
It truly is remarkable progress. But as we wrap up, maybe consider this. We've seen how AI gets smart in these specific ways, but that gap, the gap between mastering a task through learned patterns and truly understanding, generalizing, having common sense like we do,
That remains the frontier.
it's the huge frontier. So this deep dive shows the incredible mechanics of current AI training, but figuring out the what next for more human-like intelligence, that's still one of the most exciting and daunting questions out there.
Definitely something to think about. What really stands out to you from all this? Maybe it's how similar some parts feel to how we learn from feedback, or maybe it's just how fundamentally different machine perception seems to be. Something to ponder next time an AI recommends a movie or navigates you home.